Welcome to the Problems channel, season 2, episode 54, the episode which I titled Slitating or ROLIDIng bead, because in this episode we will solve a physics problem in which a point mass participates in two independent motions, sliding and rotating. But before we deep dive into the underlying physics and mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for joining our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most or the maximal academic benefit for yourself from working with the material that we present on this channel is for you to go to the homepage of this channel, and at the top of that page in the channel's trailer section, find the episode titled The Problems Channel How To. Watch that episode in its entirety. We recommend that you follow all the instructions that we give in that episode. If you have any questions, then by all means do ask them. I will try my best to find the time to answer all of your questions. And in that episode, we explain and motivate everything that we do on this channel. In the physics problem S2P2, we're given a massless rod of length L, given and known, rotating in the horizontal plane with respect to a vertical axis of rotation at a constant angular velocity omega 0, which is given. In the steady state, a point mass m, let's say this guy right here, the point mass m, a bead, is affixed to the rod, to the massless rod, in such a way that it is positioned L0 units of distance away from the vertical axis of rotation with respect to which the massless rod is executing its rotational motion, and evidently L0 is less than L strictly. This situation is happening in steady state, and then eventually at some time, let's say the point mass m was affixed to the rotating massless rod with a contraption that is attached to the axis of rotation with a thin thread, and at some point the thread is cut. At that point, the rod still rotates in the horizontal plane at a constant angular velocity, but the point mass m, the bead, begins to slide along the massless rod towards its free extremity with no friction. And in this setup, we are asked two questions. First, we're asked to recover the separation velocity Vs of the bead with respect to the rod when this bead reaches the end of the rod and jumps off that rod. Number one. Number two, we're asked to recover the separation time, let's say tau s or ts. In other words, we're in the second question, we're asked to recover the time that it takes the point mass m to slide starting from its initial displacement from the vertical axis of rotation L0 all the way to the end of the rod and jump off. And in order to set up the context of why we will be solving this particular problem in this particular way, I have prepared a little segment for you next. Across the 4 episodes shown on the board, Season 2, Episode 52, Season 2, Episode 53, Season 2, Episode 54, and Season 2, Episode 55, what we're doing is studying the mechanics of the problem-solving approach to which I refer as mathematical equivalence. In Season 2, Episode 52, we solve two problems, the 9-bottle problem and the 9-coin problem, and we show that sometimes two solutions of two technical problems come tantalizingly close to each other but still and nonetheless they fail to be essentially the same or structurally indistinguishable, which means that it is not possible to mechanically convert a solution of one problem into a solution of the other problem. Just for a quick reference, we solve both of these problems algebraically and geometrically. In Season 2, Episode 53, we take some amount of initial assumptions that apply to two fighting armies when the combat takes place in the open, in the direct view, when every opponent has the direct view of the other side. And we take that combat to be among humans, and we deduce a linear system of two ordinary differential equations of order 1, which constitute the so-called Lanchester's square law. We solve this problem in its own specific way using the initial conditions that we established in that problem. And in Season 2, Episode 54, this is this episode, we are solving the problem that deals with a point mass, or let's say a bead, that participates in two independent motions. The motion along an absolutely rigid massless rod, which in turn rotates in the horizontal plane about one of its extremities. In Season 2, Episode 55, we will inhale the solution of the problem that deals with the Lanchester's square law, the one that we cover in Season 2, Episode 53, and the solution of the problem that deals with the slitating or ROLIDIng bead. And we show that even though verbally these two problems sound very, very different, mathematically the solutions of these problems are actually equivalent. And we show how to take the solution that we develop while we solve the problem that deals with the Lanchester square law, and we apply it to the solution of this problem of the bead that slides along a massless absolutely rigid rod that rotates in the horizontal plane with a constant angular velocity. And we show how this can be done mechanically. So in some sense, we show that the solutions of these two verbally very different problems are exactly mathematically equivalent. And we will see in the previous episode, we showed how to take this specific linear system of two ordinary differential equations of order 1 and reduce that to a single ordinary differential equation of order 2. In this episode, in a few seconds, we will see that we will essentially arrive at an equation that describes the process of interest that unfolds in this problem in the following way. The equation will be basically the second derivative of a certain quantity will be expressed through that quantity itself like this. So fundamentally, across these two problems that are again verbally described very differently, here in Season 2, Episode 53, with the Lanchester square law, we dealt with fighting armies in the open, in a direct view of each other, supply of ammunition, no reinforcements, lethal skill, attrition rates, annihilation time, and on and on and on. Here, the verbiage of this problem is completely different, has nothing to do with fighting armies. This is a typical problem for a verbal theoretical physics exam, a massive bead sliding along an absolutely rigid massless rod and so on. Yet fundamentally we see that both processes of interest that unfold in these two seemingly very different problems are described with one and the same, in this case, differential equation, ordinary differential equation of order 2 that can be described as follows. And because in the corresponding branch of mathematics that deals with theory of differential equations, the bread and butter of that layer are the so-called existence and uniqueness theorems for solutions. And according to the corresponding theorem, the solution of this differential equation exists and it is unique. And that is why we will see at the end of today's episode that these two problems are equivalent, mathematically equivalent, and in season 2 episode 55 we'll show precisely how to take the solution that we developed in season 2 episode 53 and convert it into the solution of the problem that we'll solve in this episode mechanically. And the last note, it is possible to watch any one of these episodes in isolation completely without any rhyme or reason to it. But for best results, for best academic results, it is recommended to watch this episode in this specific sequence. In season 2, start with season 2 episode 52, then follow with season 2 episode 53, follow with season 2 episode 54, followed with season 2 episode 55. And now, without any further ado, let us solve the problem that deals with a bead that moves along a massless rigid rod, which itself rotates in the horizontal plane with a constant angular velocity. Just like in mathematics, an inseparable part of the culture or an inseparable part of the fabric of studying physics should be the intellectual or the mental habit of taking one and the same problem and trying to come up with as many different solutions to that problem as you can master. And we will do these experiments both in mathematics and in physics on this channel, but I do not want to overload our discussion with too many technical details. One idea per episode, one idea per problem. But on a tangent over here, for example, we can, amazingly enough, using the Newtonian formalism, deduce the differential equation of interest almost instantly by doing what? By observing the following. Let's say that the thread that was holding our point mass at a fixed distance L0 from the vertical axis of rotation was cut, and the bead started its motion along the absolutely rigid massless rod towards its free extremity. Then, if we pick the reference frame that is embedded into the rod itself, and we take the point where one of the extremities of the rod is attached to the vertical axis of rotation, we take this point to be 0. Then we can measure the evidently horizontal displacement of the massive particle away from the initial reference point O with the coordinate x. You see, and in that reference frame that is embedded into the rod itself, as shown over here, then the rod itself remains motionless. And in order to write down the second law of Newton, the famous ma, in this case, what will be in terms of the coordinate x? We will have what? The velocity of the massive bead with respect to the massless, absolutely rigid rod will be what? Will be x dot. I will use the theoretical physics notation dot to show the derivatives of the certain quantity with respect to time, and the acceleration with respect to the rod will be the second derivative. That much we remember. I will make room right now here on the bottom to write down for me, but you guys remember this. So the law of motion will be mass times the second derivative of x, where x is the quantity that I explained right here, must be generated by what? Some authors say fictitious or pseudo-centrifugal force, or the force that acts on the massive bead and pushes it away from the center of rotation O, and that will be m omega squared 0 x. Since the mass of the bead remains constant at all times, cancel it out, and voila, we have our ordinary differential equation of order 2. But some viewers of our channel asked me to see how the Lagrangian mechanics can be used, or the Lagrangian formalism, and in order to apply the Lagrangian formalism to this problem, we need to study the behavior first of the so-called Lagrangian, which is the difference between the kinetic and the potential energy of the system. In this case, it is natural to take the horizontal plane in which the rotation of the absolutely rigid massless rod unfolds to be the level where the potential energy is zero. So if the potential energy is zero in our case, and it does not change, so the Lagrangian in this case is just the kinetic energy. What is the kinetic energy of our rod? Well, if the absolutely rigid massless rod did possess some mass, then it would contribute to the kinetic energy of the system. But precisely because we take this rod to be massless, and this is again an abstraction, which means that in reality, if we were to conduct a real physical experiment, it means that the mass of the bead that moves along the rod is way, way larger than the evidently non-zero mass of the rod itself. But in this case, the kinetic energy of our system will be comprised only of the kinetic energy contributed by the massive point m, and it will be what? The moment of inertia times the omega over 2, omega squared over 2, the moment of inertia of our point mass with respect to the vertical axis of rotation. Just as a reminder, in some sense, this can be taken as a definition of the moment of inertia will be m x squared, mx squared, plus the kinetic energy associated with the motion of the bead along or with respect to here v, the velocity of the bead with respect to the rod itself. So these are two components that go into the making of the kinetic energy of our system. Now, there is one wrinkle over here in the system. Remember the so-called, there is no friction in our system. No work is being done to overcome that force of friction. So the laws of conservation of mechanical energy and angular momentum must apply. And we all remember the famous experiment where, for example, a figure skater that has the hands close to the torso spins fairly quickly around the vertical axis, but as the figure skater begins stretching the arms away from the torso, then the angular velocity or the rate of spin slows down or decreases. This is the manifestation of the law of conservation of angular momentum. In this case, the angular momentum of our bead initially will be what? M L squared 0 omega 0, and if it were to be conserved, then at a distance x from the vertical axis of rotation, what will it be? Mx squared times omega, and the question here is which omega? Look at this. The mass of the bead remains constant at all times. It can be eliminated safely. It does not vary over time. There is no reactive motion here. L0 is a constant. Omega, in this case, we take to be a constant. That means that for this quantity to be a constant, we have x. X does what? X increases somehow. X grows. This is our x. With time, it becomes larger. So for this balance to happen, the angular velocity of the bead must what? Must decrease. However, we're told that this is not the case. This is not the case. So the wrinkle here, the technical wrinkle here is, even though our point mass is moving away from the center of rotation along the rod, and it takes more effort, intuitively speaking, or in plain English, it takes more effort to rotate that mass if it's away from the center of rotation. That means that there is a carefully calibrated input into the system. I'm not really sure how this can be done practically. Maybe a sequence of gears applied to the vertical axis of rotation. They supply enough energy input into the system so as to make sure that the whole system, massless rod and the bead, whose distance grows away from the point of rotation, from the vertical axis of rotation, still remains one and the same. The angular velocity remains constant. It is possible to solve a very similar problem, basically the same problem, but without the assumption of the carefully calibrated input when the angular velocity of the system rod bead decreases over time when the system left to its own devices. So instead of spinning with a constant angular velocity, the system slows down. In any case, what do we have to do now? Well, we just have to spell out the kinetic energy in a tactically advantageous way to prepare it for what? To prepare it for our famous, again, because there is no friction, no work is being done to overcome it. So the Euler-Lagrangian equations decay into what? Just one equation, because this system possesses how many degrees of freedom? Precisely 1 degree of freedom, because one quantity is enough to completely and fully describe the motion of interest. The things that interest us can be captured with just one number, if you will, with one quantity. Consequently, our system has 1 degree of freedom. There is only one Euler-Lagrangian equation, and in this case, it will look as follows. The first complete derivative over time of the first partial derivative of the Lagrangian with respect to the generalized velocity will be equal to the first partial derivative of the Lagrangian with respect to the generalized coordinate. And we're pretty much home free. Look at this. The kinetic energy will be what? The angular momentum of the point mass, that is x units of distance away from the axis of rotation, will be mx squared omega squared 0 over 2 plus mx dot squared over 2. This is the kinetic energy of the bead moving with respect to the rod. That's it. Let us compute the first partial derivative of the Lagrangian with respect to the generalized velocity. What do we have? Well, in this case, the generalized velocity is this term. This term is treated as a constant. It's gone. Its derivative will be 0. And what do we have here? Well, 2 and 2 cancel each other out, and we have our mx dot. That much should be understood. 2 goes into the numerator, 2 in the numerator and 2 in the denominator cancel each other out, mx dot. And if we take the first full derivative of this result over time, what will we have? Well, theoretically, we have a product of two functions, a function called m and a function called x dot. So by the rule of computing the first derivative of a product, what will we have? We will have m dot times x dot plus mx dot for the second derivative. But the mass of our bead remains constant at all times. It's one and the same. So this term disappears, and we only have left mx dot dot, the second derivative of x, of the horizontal displacement of the bead, with respect to time, mx dot dot. That much is straightforward and should be understood by everyone. Pretty much game over. What do we have to do? We have to just compute the first partial derivative of our Lagrangian with respect to the generalized coordinate. In this case, the generalized coordinate only factors into the kinetic energy or the Lagrangian in this term. It means that this term treated as a constant, its derivative with respect to x is gone. And what do we have here? 2 goes into the numerator, 2 in the numerator, 2 in the denominator cancel each other out. What do we have? mx omega. So let's write it down here. The first partial derivative of the Lagrangian with respect to the generalized coordinate is what? mx omega squared. mx omega squared omega 0 squared. And this is it. We now equate this result to this result. And look, we have what? mx omega 0 squared is equal to mx dot dot, second derivative. So this is precisely this result. This is equal to this is this. Now, let us carefully note that the mass of the bead remains one and the same. One and the same. This is the ordinary differential equation of order 2 that we are about to solve fairly rapidly. And we solved a similar equation in the previous episode, in season 2, episode 53. If you missed it, again, I recommend that you watch it. I will show again in great detail how to solve these equations by hand, but I will step fairly rapidly. Those of our viewers who watched the previous episode, the season 2 episode 53, already know that in the world of differential equations, or in the world of ordinary differential equations, there exists a separate class of differential equations in which variables can be separated, and this class of equations is called equations with separable variables. And in the previous episode, in great detail, I showed how to deal with these equations. And again, one of the reasons why these type of problems are perfect examples of problems that are given on the verbal theoretical physics exam is because in my time, for example, professors knew obviously all too well that that solution can be unfolded in real time in a space of 15-20 minutes, and that is why you're asked to solve this problem and present that solution. That is the solution that the professor wants to hear from you. And sometimes when people, for example, I remember still in Quora, say, oh, Roman, why are you doing all these crazy complicated things? Just assume the solution of this differential equation has the form some constant times some exponent or a collection of exponents. And my question to this all the time, if I give you another hairy differential equation which you never saw in your life, where did this assumption about the shape of the solution come from? How would you guess it? So the question is, if something can be solved analytically using your own mathematical wits, your power of improvisation and your power of mathematical imagination, then as a student you should always do that. And this is precisely what the people who organize the curriculum know, and that's what they expect from you to that end. The idea of solving these type of equations, which is an equation with separable variables, is to separate the variable x from the variable t, the very independent variable of x, time. And that is can be done in this case in two stages. In the first stage, we separate the first derivative of x from x, and then in the second stage, we separate x from the variable t itself, from the time, and thus we obtain the function x of t. So the way these things are done, again, this is not something that's horribly complicated. If you're in high school, you should be able to generate these ideas yourself. So first, we spell out the definition of the second derivative of a certain function over time. What is that? Well, the second derivative is the first derivative of the first derivative. As such, we write x dot dot x dot dot is equal to dx dot over dt, and that is equal to what? That is equal to omega squared 0 x. You see, so far nothing complicated. We pivot right on the material that we're given. We stare intensely, as Isaac Newton used to say, upon thinking about it. This is what we do. What is the next maneuver? Multiply both sides of this equation by one copy of the first differential dt times dt times dt. What will happen on the left hand side? Cancel, cancel. But this differential, first differential, stands. So now we have dx dot is equal to omega squared 0 x dt. What is the next step? Again, use this as an opportunity to think on your own. Put this video on pause, walk away, try to predict the next step, the next fruitful step. If you invent a better one, let us know in the comment section. The next popular successful maneuver here is multiply everything by one copy of the first derivative of x. And when we do that, what will happen? Well, here we will have times x dot, and here we will have times x dot. This is all real numbers, unlike quaternions that in general do not commute on the multiplication. Real numbers do, so here we can do that. So what is the next step? Well, the next step is to leave the left hand side of the result alone, because here we're done. We're operating in terms of velocity, so we can integrate this animal from the initial velocity to the current one. Some magic has to unfold over here. What is that magic? Again, pretty much the only thing you can do over here is spell out the definition of the first derivative of x over t, which is what? Dx over dt. Exactly. Now what happens? Dt in the numerator, dt in the denominator cancel out. And what do we have? Gone, gone. What is left? Jam this guy in here. And what do we see? We have the following wonderful expression. And the first stage, remember, the first stage of separating the first derivative of x from x is gone. Again, in different problems, these symbols will mean different things. Maybe it will be amoebas multiplying in the petri dish, or it could be, I don't know, animals, predators chasing after prey. It could be a different thing, but fundamentally, essentially, the mathematical essence will lead you in this direction. And this is where I will take a break, because in the next segment, we will do something that's specific to this problem. We will integrate this result over the boundaries that are specific to this problem. And that is what we will do next. Now we will carry out the second stage of separating the variables, and before we do that, we integrate both sides of this relation with specific boundaries. Initially, what was the velocity of the bead with respect to the rod? When it was fixed at a distance L0 from the vertical axis of rotation, it was not moving relative to the absolutely rigid massless rod. And that means that the initial velocity was zero, precisely zero, to the current one, x dot, to the current one. Let me erase this maybe so it doesn't confuse you guys. You understand how all these things transpired. You understand how this works. We already are doing it for the second time. So till x dot, and here from L0 to what? To the current position of the bead on the rotating rod. And don't forget that our rod is absolutely rigid, which is again an abstraction and idealization. In real world, there is no such thing. Physical, if we were to conduct a physical experiment, our rod during the rotation, depending on how fast it rotates, it will stretch a little, its length will increase. But because in our case, remember, in physics, we are looking for an exact solution of an approximate problem. So this is our approximation. Now, these integrals over here come out to be trivial. The fact that this thing is kind of looks funny for some people, still fundamentally you have what? Fundamentally you have the integral that looks like this, t dt, or pick your other favorite dummy variable. So this is t squared over 2 plus a constant. We do not want to deal with the constants. We apply the well-known and understood boundaries of integration right away. This is perfectly normal. So what will we have in this case? Let's write down the result maybe over here on top. What will we have? We will have on the left hand side, we will have x dot squared over 2 evaluated between 0 and x dot must be equal to omega squared 0 x squared over 2 evaluated between L0 and the current value of x. You see, from here, x squared over 2, x dot squared over 2, x squared over 2, multiplicative constants. So this much is understood. This much is understood. So from this relation, what do we have? 2 and 2 cancel each other out right away. So we have x dot squared minus 0 is 0, and that is equal to omega squared 0 x squared minus omega 0 squared L0 squared. You see, I just opened up the parentheses on the left hand side here. If you remember your calculus course, that will be x squared minus L squared. This is all baby arithmetic. And now what? Well, when we take the square root of both sides of this results, what do we have? Here, technically, x dot will be equal to plus minus x plus minus, let's say omega 0 squared. Omega 0 squared is the same thing. Factor it out. Omega 0 times the square root of x squared minus L0 squared. But across two roots, which one we take and why? Well, in this case, x increases, so the first derivative must remain what? Positive. Exactly. That is why we take the root with a plus sign in front of it. We omit that plus sign, but maybe just because we want to be good citizens of mathematics, we will put the plus in front of it. What is the next and the final step, pretty much? Exactly, we spell out the definition of the first derivative yet again. What does it mean, x dot? Well, that's dx over dt. And now what? We multiply both sides of this equation by dt. So this will be times dt times dt. dt and dt in the numerator and the denominator on the left-hand side of the equal sign will cancel out. This is, well, I'll keep it so that you guys see the evolution of this thing. What will happen? dx is equal to omega 0 with the plus sign, square root of x squared minus L0 squared dt. And voila, what do we do here? Well, we move this square root over here this way, because there is no material that connects to t. All the material here only deals with x, and this is the magic of separation of variables. Now we're done. Pretty much all we have to do now is write down one equation that represents, I will erase all these guys and prepare it for the next segment, but all we have to do now is write down one equation that represents the fact that we did separate the variables. Let's see. Dx divided by square root of x squared minus L0 squared equal to omega 0 dt. You see, we separated the variables. That's the victory. Of course, yes, once you begin studying differential equations, you will realize this is a toy case. Most of the time, even if and when a given differential equation is of type separable with separable variables, the intermediate integrals will usually be not elementary, which means that these integrals will not be representable as a finite combination of elementary functions. Sometimes we can reduce these integrals to non-elementary, for example, non-elementary functions that can be done analytically and symbolically, and sometimes the integrals come out quite complicated and they need to be solved, let's say, numerically. So this is the equation that represents the separation of variables. All the material that deals with the generalized coordinate x on the left-hand side or on one side of the equal sign, all the material that deals with the independent variable t on the other side of the equal sign. Again, usually the integrals on either side come out quite horrible. not elementary at all. But in this case, again, precisely because all the integrals are baby integrals, they come out as elementary. That is why these problems are given on the verbal exams. And again, I will leave you guys with this form. In the next segment, we will begin integrating with specific boundaries, but this is the general form to which you want to reduce your equations with which you will be dealing in other problems, preparing them after separation of variable for integration. And in the next segment, we will do precisely that. We will integrate this relation shown behind me using the boundaries that are specific to this problem. Before we move on to integrating the relation shown over here over the boundaries that are specific to this problem, I will give you guys one hint. Remember, a few seconds ago, we had the following equation over here. The first derivative of x was equal to plus omega 0 square root of x squared minus L0 squared. That much we did use. That was our intermediate steps. And for example, when I was solving this problem, amazingly enough, I kept good record, and that record over here helped me a lot at some point. Again, if you're practicing theoretical physics, you're expected to at some point take off the head that reads theoretical physicist and put on a head that says a wily mathematician. You will come back. I will come back to this relation shown over here when we will be answering the first question of this problem. So keep track of that equation over here and give it some number. Let's say, because we are dealing with the velocity, I'll give this equation number 5, the Latin number 5. So this will be equation number 5. I will call your attention to this equation in a small number of minutes when we will technically solve this differential equation. So consider this a hint. So now, what do we do here? Here we integrate this equation, this result. We integrate both sides. Again, we can treat this integration in the indefinite form, come up with the constants, merge them onto one side, and then try to recover the value of that constant using the initial conditions. But here the things are straightforward. We do it right away. On the right hand side, we integrate from 0, because this is where we started the timer, when the time started ticking, as when the thread that was holding the bead in a fixed position with respect to the vertical axis of rotation in place and was not letting it slide. But when it was cut, the timer was launched. Boom, 0 to the current value. This is the current value of time. And on the left hand side, we integrate this result between which boundaries? Well, the initial position, this integration is carried out with respect to the generalized coordinates here, x. So the initial position was L0, and what is the current position? Well, the current position is x. Thus, if we succeed in computing all the integrals that we arrive at, again, here we arrive at baby integrals. Usually that is not the case. The integrals come out quite horrible, but if we can integrate analytically and in closed form, that is a miracle, and voila, we will have our x as a function of t, and this is precisely what we will do next. As we integrate the given function omega 0 dt from 0 to t, in my notation, to some students who are new to mathematics and physics, that may be confusing, but my suggestion is that you grow up mathematically in terms of physics and put your mind into a state where it's not confusing, because in grown-up world, this is business as usual. And if this is still confusing, that maybe As you grow up, you take the upper boundary to be, for example, tau. It doesn't really matter. Execute the integration and then dispense, rename the variable tau into t. But here, the dummy variable can be called anything you like, but I keep these variables in order to show how the fabric of the solution is weaved and how the results are obtained. So here we will have, what is the result? The result is a trivial integral omega t evaluated from 0 to, let's say, tau. This will be omega 0 tau. And once you made peace with everything that transpired, then you can simply rename tau with t, tau with t, and voila, you have your result. The right hand side of our relation becomes equal to omega 0 t. As we deal with the integral that we saw on the left-hand side of our final separation of variables equation, we will deal with this integral in the indefinite form. At least that's how I will do it. If you have better ways, you can do it in a different way. But here, remember, we have the difference of squares, and in the previous episode, in season 2, episode 53, we dealt with a similar integral that dealt with the sum. But remember, we are solving these two problems pretending that we know nothing about the idea of mathematical equivalence, and we're in the process, in the mock process of mock discovery, if you will, of this very powerful idea of mathematical equivalence. So we pretend we do not know anything about the existence of the other solution, and we solve every problem in complete isolation from anything else in the world. This is highly custom tailored, bespoke, if you will, solution for this particular problem without the attraction of any new ideas. We see the problem, we deal with it in this specific way. So again, in the previous episode, we used the essentially the substitution that amounted to the hyperbolic sign. Again, this idea is due to the Swiss-born mathematician Leonhard Euler. In this case, we will use the substitution that is essentially the hyperbolic cosine. So here we will put x equal to L0 e to the power z plus e to the power minus z over 2. Under this specific substitution, and again, I see even on Quora, I saw all sorts of people shooting from the hip, so to speak. We don't care about this. The thing is, as you are building yourself up as a mathematician and or theoretical physicist, there is no other way. You have to work, in my view, you have to work with the basic definitions of these functions, because otherwise you will never really understand why they work the way they do. And at least once in your lifetime, you should be able to generate all the relative proofs on the properties of the hyperbolic functions on your own by yourself to see how this works. And I think I have an idea of putting together an episode for you guys where I will show the discovery of the hyperbolic trigonometric functions, the hyperbolic cosine, hyperbolic sine in the Western civilization in Europe. And I think, if I'm not wrong, in one of the texts by Euler shows the details of how de Moivre did it. So anyway, here the first differential of dx under that substitution is what? Dx comes out to be, again, L0 e to the power z minus e to the power minus z over 2 dz. You see, this is the first differential based on this. Now, let us compute this animal right here separately. Let's do it over here. X squared minus L0 squared comes out to what? L squared, L0 squared, and L0 squared can be factored out right away. We can do it in our mind's eye. We don't really need to use pen and paper, but for demonstration purposes, let's do that. We can actually evaluate the whole integral in our mind. No pen and paper once we see this in our mind's eye. the underlying arithmetic is more than straightforward. This is where the technical wits are. Everything else is not mathematics, computational calisthenics. So here, when we construct the difference of squares, what will we have? We will have e to the power twice z plus 2 plus e to the power minus twice z. Here we have negative sign, so here we will have minus 4, and that whole thing is divided by 4. And what do we see? We see that L0 squared comes out equal to what? Plus 2 minus 4, negative 2, and then that whole thing unfolds back into what? That whole thing unfolds into the difference that we see over here. In other words, we will have e to the power z minus e to the power minus z over 2, and that whole thing squared. You see, this is exactly the magic and the wits of Leonhard Euler. His substitution over here does what? When we compute our integrand in terms of the new variable z, what will happen? Well, dx here will be divided by the square root of this horrible thing, square root of this horrible thing, and square root of this horrible thing. But this is a perfect square. And when this perfect square is unfolded, it becomes what? It becomes exactly that. That means that when dx in terms of dz is divided by the square root of the difference of squares, what will we have left? We'll have left nothing but dz, and this is triviality itself. This is equal to z plus some silly integration constant, and now all we have to do is perform the reverse substitution and obtain an equation that expresses the new variable z in terms of the original dummy integration variable x. The objective now is to express z as a function of x, or technically we need to find the inverse function of the hyperbolic cosine. The way we do it, you should be able to do on your own. This is not complicated, but the arithmetic here is as follows. We multiply this relation over here through by 2, 1 copy of 2, and divide it by L0. L0 is not 0, and what will we have? We will have e to the power of z plus e to the power minus z equal to 2x over L0. Then we multiply this equation through by e to the power of z, and then we move the resultant term to the left hand side. What will we have? E to the power twice z minus 2x over L0 e to the power of z plus 1 is equal to 0. That maneuver is straightforward. Again, if you do not see this right away, then you need to learn how to see these things. Usually, you can introduce another variable and name e to the power of z something else. But for example, as a hint, you can rewrite this exponent which way? You can rewrite it like this: e to the power of z, and then the whole thing squared. And then we will have basically the good old quadratic equation in the exponent e to the power of z. We know how to solve these equations right away. We write down its two distinct roots. E to the power of z 1, 2 is equal to negative b over 2, so that will be x over L0, and then plus minus square root of, let's think about this together. The square of b becomes 4x squared over L0 squared. Subtract what? 4 times a times c, which is 4. 4 carried out in either summand. Square root of 4 is 2. 2 over 2 is 1. Nothing is left over here. So all we have here is the following expression. X squared over L0 squared minus 1 and the square root. So now we need to decide which of these two, between these two signs, which one do we take, plus or minus, and why? Well, in reality, remember this. Let's maybe appeal to a graphic argument, if you will. If this is one expression here, what is this? Z, this is X in our original form. We have it scaled somehow, but let's say we omit right now. Let's say L0 is 1 unit. So, or why not? So this will be our original. This will be our original form. It looks a little tricky to draw. Looks like a parabola. It is not. This is L0. This is L0. And then over here, technically, we have two branches. We will have two branches. If we now, what do? If we take the natural logarithm of both sides of this result, what will we have? Well, then we will have the following. Z is equal to base E logarithm of this here result. And this plus minus over here means what? That technically the inverse of the hyperbolic cosine is not a single valued function. This function can be, let's say, what is it? It looks like two valued function, if you will. It can be represented as a composition graphically of two continuous and single valued branches. One branch that corresponds to the plus will run this way. This is again will be L0. Well, it looks this way. And the other branch, well, let's put it this way. This will be logarithm of what? Something x over L0 plus square root of x squared over L0 squared minus 1. See, this is the positive branch, so to speak. And let's see, let's do it. Which color can you see better? Yellow. Let's do this in yellow. And this branch will run this way. This will be the negative branch, log of x over L0 minus square root of x squared of L0 squared minus 1. You see, minus for this branch, and where's my blue? Plus for this branch. You see, this is how things work. But what is going on in our case? In our case, x varies this way, corresponds to which corresponds to this branch over here. I'm not sure if that's convincing for you guys. If not, let's then have a discussion in the comments. But the idea here is that we take the positive sign over here that represents this blue branch over here, this branch, this part, which corresponds to the change of the x coordinate this way, this one, this part right here. And to cut the long story short, between two, in other words, between two signs, we pick this one, the plus sign. So there we have it. This is our result. This is our result. We pick the positive, the root with the positive, with the plus sign. And we can now take our z and put it back into the original indefinite integral. Hindsight is always perfect. As I was erasing the board and preparing for this segment, I realized that a few seconds ago, remember we had the expression e to the power of z equals plus or minus, but evidently e to the power of z always remains positive. And in that sense, in the original function, we have this representation for the positive when z is strictly positive, it is this branch. But when z is negative, then we have this branch in the inverse. Of course, we have to change these letters, but you guys understand what's going on. This case, so this branch corresponds to this piece right here. E to the power negative z minus z is this guy. And evidently, once we have the expression e to the power of z equals this, we pick the upper sign, we keep the plus sign. So in any case, what we have now is the following. We have this expression, we put it for the result for the definite integral, which we evaluate between the boundaries of L0 and the current value of x. We put this into this expression. The boundaries of here fall out as follows. When x is equal to L0, we have what? L0 squared over L0 squared is 1. 1 minus 1 is 0. Square root of 0 is 0. Gone. X is L0. L0 over L0 is 1. The natural logarithm of 1 is 0. So the minus in our favorite calculus formula disappears, and only the input from the upper integration boundary survives, and that's precisely the result. The natural logarithm of x over L0 plus square root of x squared over L0 squared minus 1. And now we have a full, complete analytic closed formula, some people say, expression for the left-hand side of the integral of our original equation. And now we can equate the left-hand side to the right-hand side. Now that we managed to evaluate integrals on either side of our complete separation of variables equation successfully, and we managed to do it in an elementary way, which again is a miracle. In most realistic situations, it will never happen. All we have to do now is separate the variable x from the variable t and write it down explicitly as an expression or as a function of t. The way we do it is as follows. We will potentialize both sides of the equation. In other words, we will write down the following expression: e to the power of log equals e to the power of omega 0 t. On the left-hand side of this potentialization, we will have the expression shown over here. And on the right-hand side, we will have the exponent e raised to the power omega 0t. That much we understand. What is the next maneuver? Move this term to the right-hand side of the equal sign. We will write down minus x over L0. What is the next maneuver? Square both sides. Square the left-hand side, square the right-hand side of the equal sign. What will we have here on the left-hand side? Well, the square will simply annihilate the square root sign. We will have x squared over L0 squared minus 1 equal to e to the power twice omega 0t minus 2x over L0 e to the power omega 0t plus what? Plus the square of the ratio of our usual suspects, x squared over L0 squared. What do we see now? The ratio of squares cancel themselves out. What do we have? Once you understand this maneuver, let me erase this here and erase this here. We understand the genesis of all this wonderful stuff. What is next? Well, next is -1 flies to this side over here, +1. And what about this guy? this guy flies. Let's write it down suggestively. X times 2 over L0 times e to the power omega 0 t is equal to this thing, and this thing is gone. This thing is gone. So what do we have now? Well, before we do anything else, let me write it in a more compact way. Plus 1, let's multiply both sides of this equation by the negative exponent minus omega 0 t. What will we have? On the left hand side, when the e to the power omega 0 t collides with e to the power minus omega t, they will annihilate each other. This is gone. This is gone. What will happen on the right hand side? Well, one copy will be eaten away by the minus, by the negative. So we will have this is equal to e to the power omega 0 t. Here will be plus this exponent plus e to the power minus omega 0 t. So this is gone. We understand how this came about. And what is the last thing to do? Multiply this equation through by one copy of what? Inverse of this L0 over 2. Here, 1 we can safely eliminate and write it down x of t equal to L0 divided by 2, and this is our expression. Let me maybe put it into a red box that you guys, so that you guys can see. What will we do next? Well, now that we have an explicit solution for the change of the coordinate x of the sliding bead as a function of time, we can compute its first derivative or velocity and second derivative or acceleration. On the one hand, I do not want to insult your intelligence and tell you how to compute the first derivative of an elementary function. On the other hand, just for the benefit of everyone, let us do this together. The first derivative of x, or let's say the velocity of our moving bead as a function of time, will be given by the first derivative of the sum will be omega 0 times the exponent in the first case and minus omega 0 times the exponent. The omega 0 will be one and the same multiplicative constant, so once we factor it out, we will obtain the following expression. Omega 0 L0 times e to the power omega 0 t minus e to the power minus omega 0 t over 2, and this is our expression for the velocity of the bead with respect to the absolutely rigid massless rod as it chases or races its way towards the free extremity of that rod. The acceleration of the bead relative to the rod can be computed either by calculating the second derivative of the coordinate of the bead as it chases towards the free end of the absolutely rigid massless rod, or by computing the first derivative of the first derivative. And once we have done all this heavy lifting already, let us just do that, work with the expression for the velocity of the bead as a function of time relative to the rod itself, and write down this expression there. A, that is the second derivative of x over time, will be what? The first derivative of this exponent will be simply omega 0 times the exponent, because the differentiation is carried out with respect to the variable t. So this will be omega 0 times this exponent. The first derivative of this exponent will be what? negative or minus omega 0 t, because we have the minus sign in front of it, and minus from this factor and minus in front of this exponent. Negative 1 times negative 1 is positive 1. So here the positive, the plus sign will percolate, and one copy of omega 0 as a common factor between two summas will be carried out. It will collide with this one copy of omega 0, and what will we have here? Two copies, or omega 0 squared. So we will have here omega 0 squared L0 times, let's write down the exponents carefully, omega 0 t plus e to the power minus omega 0 t divided, the whole thing is divided by 2, and this is our result for the acceleration of the bead relative to the absolutely rigid and massless rod. And now, as a sanity check, as a purely mathematical validation of all the work that we have done so far, let us, for example, we'll take the hat that reads a physicist off, put it on the table, put on the hat that says just a mathematical inclined thinker. With the mathematicians in the room, the question is, can we look at the expression for the second derivative of x and recognize in the midst of the material that is the second derivative our original expression for the x of t, the coordinate? Well, evidently the exponents over here, the linear combination, is the same here, it is the same here. One copy of L0, one copy of L0. So this way, what do we have? Well, we have x of t, and what do we have in front of it? Omega 0 squared. So from this expression over here, it follows what? What do we have? We can write down formally, purely mathematically, without analyzing any forces, reference frames, fictitious or pseudo forces, this and that, yada yada, none of that. Just purely mathematically, we have omega squared 0 times x. And this is the original equation that we started from. So on the surface, it looks like, as a technically oriented person, you're never happy, you're never absolutely sure, there's always a degree of doubt, but you think, at the first level of approximation, it looks like we did the right thing, and it is plausible that our result is correct, because again, through all the work that we have done, purely mathematically, purely formally, our result seems to be validated. So we have validated our result, and now we can answer the questions that were posed in this problem to begin with and find the separation velocity and separation time of the bead when the bead finally jumps off the rotating rod. The separation velocity of the bead when it jumps off of the free edge of the rotating rod can be recovered in two different ways. In one way, that velocity can be recovered in a straightforward manner, but that manner will be very computationally intensive, and unfortunately that is what many students do when they come to that point in solving this problem. The other way, with a little bit of wits applied to the problem, the velocity, the separation velocity of the bead can be obtained almost instantly. And that is one point I want to drive home and stress, that every theoretical physicist is one mean part-time mathematician and thinking out of the box. When you work in the capacity of a theoretical physicist is pretty much a requirement. The pressure or your ability to show your technical skill, improvisation, and ingenuity is relentless. It never ends. You always are looking for a clever way to do things, and here is the deal. I will say a few more words about the separation velocity when we get to it in a few seconds, but here is the deal. Remember, I told you guys the equation number 5 with the Latin V, equation number 5. That was actually one of the steps during which we used in order to develop our solution. We had the following expression. obtained. When we were separating variables, we came to this idea: x dot equals to omega 0 square root of x squared minus L0 squared. That much we had. That was the equation number 5. I remember a few segments ago I told you at some point I will call your attention to this intermediate result, and that is why it is also important to keep your intermediate results neat. Write them down in the same way so that you can go back to your records and see, oh, that's where it is. This is helpful. So this is it, game over. The separation velocity of the bead when it jumps off the free extremity of the absolutely rigid massless rod when it gets there is given by this formula over here. So the separation velocity Vs will be equal to simply omega 0 square root of L squared minus L0 squared, and it is obtained when in this expression over here, x dot, as a function of x, we put x equal to L. You see, when we put x equal to L in this expression, in this formula, then all of a sudden that means that our bead has reached this point right here, L, the length, and this is precisely the answer to the first question. What is the separation velocity? This is our formula. Again, give it a name, remember it. We'll come back to this here formula in the next episode when we will be converting the solution of the problem that dealt with the Lanchester square law into the solution of this problem mechanically. Again, I will call your attention to this formula, but now we can compute the time that it took the bead to basically race all the way to the end of the absolutely rigid massless rod and jump off of it. With the bead separation time, the story is exactly the same. It can be computed in two distinct ways, straightforwardly but computationally intensively, or in a much less computationally intensive way. So the first way will be simply to put L into the formula shown over here, meaning that the bead, the coordinate of the bead, has reached the end of the rod, and then solve the resultant equation L equal to L0. And the moment we do that, these times over here, these times, they become T sub S, the separation times. But being a little bit more wily, so to speak, about it, and again, this is the reason why it pays to keep your records in a sane way and do not write haphazardly, upside down, left to right, diagonally, which is many people do, me including. I'm no exception. In an adrenaline rush to solve the problem, I usually scribble all over the place. This is a bad idea. It is much better to keep your records neat. And remember, this time I didn't call your attention to it because I figured you guys will figure it out on your own. You will see it on your own. But remember, when we separated the variables one more time and computed the integrals, integral of omega 0 dt on the right hand side and the integral of dx over square root of x squared minus L0 squared, when we evaluated both integrals, we came down to the following, we obtained the following result, that the log of x over L0 plus square root of x squared over L0 squared minus 1 was equal to omega 0 t. Remember that result? Yes, you do remember if you go back and if you rewind this episode to the segment where we obtained that result before we chase forward. This is actually how we came up with this result. So some students who obtain these results and then blindly plug in x equals L on the left hand side and then solve this equation for t of s, they're doing in some sense completely legal and valid thing. This is how we do it, but again, this is not the way in which we show our ingenuity and our wits. We simply go to this result, replace x with what? We replace x with L, and the moment we do that, the t over here becomes what? Becomes t sub s, the separation time. Consequently, let me use maybe the red chalk. The moment we have it, we do what? We write down the result that t of s, the separation time, is equal to 1 over omega 0 times the natural logarithm of what? L over L0 plus the square root of L squared over L0 squared minus 1. You see, this is it. It's that straightforward. Now, once we obtain this result, shown here in red, once we obtain this result, again, I suggest that you guys number this result, give it a name, remember it somehow. I will call your attention to this formula also in the next episode when we will be doing the mechanical conversion of the solution of one problem into the other. But here's a few words about students who do not really pay much attention, but still they do the right thing. Eventually, yes, you will do the right thing. You will obtain the correct results. The difference here is in the length of the road. Walk far, get there tired, and get there. Or take somehow clever shortcut and get there less tired. So once in the sequence, we basically first we do what? We put x equal to L, solve the result for t sub s, we obtain this result, and then we do what? In order to recover the separation velocity, once we put the separation time, ts, into the formula for the velocity, then yes, here on the left hand side automatically we get v sub s equal to omega 0 L0 e to the power of omega 0 times what? Times this horrible expression minus the e to the power negative omega 0 times this. And I suggest again, once in your lifetime, you should carry out this computation. Before, while I was preparing this episode, I did it myself. It works. It's tedious, middle school arithmetic, but it's not very clever, but it still works. Omega 0 and omega 0 cancel out. E to the power of log gives you this expression. Here it will be 1 over this expression. With 2's and everything, once you do the right thing, you will come across this wonderful, to give you a heads up, you will have the following expression. You will deal with cubes. You will see L cube over L0 cube. But amazingly enough, these cubes of these ratios in this long and tedious route will cancel out. And again, you should witness the magic of obtaining this result in two distinct ways. But now we have all the results on the books. This is it with the problem S2P2, with the physics problem, with the second physics problem of this season, and we will move on to a new challenge next. Whether you did it the long and the hard way by plugging in the separation time of the bead into the formula for the velocity of the bead over here and fighting out the underlying middle school arithmetic and obtaining this formula for the separation velocity of the bead, or you did it in a slightly more clever and less computationally intensive way, still you will obtain one and the same formulas for the separation time of the bead shown over here and for the separation velocity shown over here. These results should agree no matter how you obtain them. But remember, every theoretical physicist is a part-time mean mathematician, so you're expected to show your ingenuity and creativity at all times. That pressure to be creative and show ingenuity and improvise is always on. It's relentless, it never stops. So the challenge of the next mathematical problem, S2E54, we will cover this problem in the next segment, is precisely to take the solutions that we developed in the previous episode that was the problem S2M53, and that was covered in the season 2, episode 53. And see how these solutions that dealt with the fighting armies problem, that capture the essence of the so-called Lanchester square law, can be converted into these answers over here, shown these two formulas, mechanically by twisting a few knobs and pulling a few levers. But again, this twisting and pulling is not very clever, it's just purely mechanical, which, remember, we failed to do in season 2, episode 52, when we solved the 9-bottle problem and the 9-coin problem. And that was my idea. First, we see how, when, and why things do not work. And now we're witnessing exactly how, why, when things do work. If you will be able to obtain these results from the results of the Lanchester square law problem on your own, you will witness the following idea. Back in season 1, episode 1, if you go back, remember season 1, episode 1, that was the opening season on this channel. I give you guys two distinct but equivalent definitions of mathematics for people who will never deal with mathematics in their professional or semi-professional capacity ever in their life, except for being tortured in middle and high school. Mathematics, what mathematics is an art of telling a story of how and why. For people who will be dealing with mathematics in professional capacity, earn higher and higher degrees, mathematics is an art of, not only is an art of telling a story of how and why, but mathematics is the study of structure divorced from any specific context. So initially, this definition is bewildering definition of mathematics. What does it mean? Study of structure divorced from any specific context. But if you will be able to pull this miracle of abstract thinking and translate the solution of the Lanchester square law problem into the solution of the slitating or ROLIDIng bead problem on your own, you will precisely witness that very essence of the idea that mathematics is also the study of structure separated or divorced from any specific context. And this should make it, this experiment should make this definition more clear and more tangible. Now, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the problem S2M54.